Right now, gravity is pulling you toward the Earth. You don't notice it. You never have to think about it. Yet every second of your life, an invisible phenomenon is deciding where you stand, how planets move, how stars are born, and why galaxies don't simply drift apart into nothingness. But here's a question almost nobody asks. What if nothing is actually pulling you? What if gravity, the force we've trusted for centuries, isn't really a force at all? What if everything we've ever called gravity is only the visible shadow of something much deeper, something hidden beneath the fabric of reality itself? That idea sounds impossible, and yet some of the world's leading theoretical physicists are seriously exploring exactly that possibility, because after more than 300 years of studying gravity, after predicting eclipses, navigating spacecraft across billions of kilometers, detecting ripples in space-time itself, we still can't answer one deceptively simple question. What is gravity? Not how it behaves, not how to calculate it, what it actually is. And the search for that answer has led physicists somewhere completely unexpected. Not toward matter, not toward energy, but toward information. In our previous episode, we explored an idea that sounded almost unbelievable. What if space itself isn't fundamental? What if the smooth, continuous space-time we experience every day isn't the deepest layer of reality, but an emergent phenomenon, a projection arising from something even more fundamental? It sounds like science fiction, but ideas like the holographic principle and quantum information theory suggest this possibility is worth taking seriously. If that's true, then gravity suddenly becomes far more mysterious. Because, according to Einstein, gravity isn't something that exists inside space-time. Gravity is the geometry of space-time itself, and the two are inseparable. So if space-time itself emerges from something deeper, gravity must emerge too, and that's where one of the greatest mysteries in modern physics truly begins. To understand why physicists are questioning gravity today, we first have to travel back more than 3 centuries. The year is 1687. Europe is in the middle of a scientific revolution. Astronomers can predict the motions of planets. Mathematicians are discovering entirely new ways to describe nature. But one question still remained unanswered. Why do things fall? According to legend, Isaac Newton watched an apple fall from a tree. Whether that story is literally true isn't what matters. What matters is the question it represents. The apple falls. The moon doesn't. Why? Newton realized something astonishing. Perhaps the same invisible phenomenon causing the apple to fall is also keeping the moon in orbit. Maybe Earth is pulling on the apple while the Earth and the moon are pulling on each other at the very same time. It was an extraordinary leap of imagination. For the first time in human history, the heavens and the Earth were governed by the same law. Newton expressed that idea with one elegant equation. Every object with mass attracts every other object with mass. The greater the mass, the stronger the attraction. The farther apart two objects are, the weaker that attraction becomes. That single insight transforms science forever. Suddenly, the falling apple, the orbiting moon, the planets circling the sun, and even the paths of distant comets could all be explained by one universal law. It remains one of the greatest intellectual achievements humanity has ever produced. But Newton himself wasn't completely satisfied. In fact, one aspect of his own theory deeply disturbed him. Imagine the Earth floating through empty space. Now imagine the moon, nearly 400,000 kilometers away. How does the Earth reach across that enormous distance and influence the moon? There are no ropes, no invisible beams, nothing physically connecting them. Yet somehow, gravity seems to act across empty space. Newton could calculate the force with astonishing accuracy, but he couldn't explain the mechanism. What actually carries gravity? How does one object influence another without touching it? In one of his letters, Newton admitted that the idea of matter acting across empty space without any physical intermediary seemed so absurd that he could not believe nature truly worked that way. His equations explained how gravity behaves, but they never explained why. For more than 2 centuries, physics accepted that mystery. The equations worked. Ships crossed oceans, engineers built bridges, astronomers predicted eclipses with remarkable precision. Few people worried about what gravity actually was until one man challenged the entire idea. His name was Albert Einstein. In 1915, Einstein proposed one of the boldest ideas in the history of science. He argued that Newton had been looking at gravity from the wrong perspective, not because Newton's equations were useless. In fact, they still work extraordinarily well for everyday situations. But according to Einstein, Gravity isn't a force pulling objects together. Instead, mass changes the shape of space and time themselves. Imagine placing a heavy bowling ball on a stretched rubber sheet. The sheet bends beneath its weight. Now roll a small marble nearby. The marble curves toward the bowling ball. At first glance, it looks as though the bowling ball is pulling the marble, but it isn't. The marble is simply following the curved surface beneath it. Einstein suggested that our universe works in a remarkably similar way. The sun doesn't pull the Earth, the sun bends space-time itself, and the Earth simply follows the straightest possible path through that curved geometry. Gravity isn't really a force, it's geometry, and when Einstein first introduced this idea, it sounded almost unbelievable. Darun was eigen fikje ami Netflix documentary. Final cut mayan biai roachkeb. Nice part 2, sampun voice over ready. Kono hedin ba editin not chaad a. Dilam. And yet, as unbelievable as Einstein's idea sounded, nature kept proving him right. Just 4 years after he published general relativity, an opportunity appeared that would change physics forever. In 1919, a total solar eclipse allowed astronomers to test one of Einstein's boldest predictions. According to his theory, gravity doesn't only affect planets, it bends light itself. During the eclipse, the moon blocked the sun's brilliant light, revealing stars that normally couldn't be seen during the day. If Einstein was correct, those stars shouldn't appear exactly where they actually were. Their light would curve as it passed near the sun's, making the stars appear slightly shifted across the sky. It was an incredibly tiny effect, barely measurable. Teams of astronomers traveled across the world, carrying fragile telescopes and glass photographic plates, hoping the weather would cooperate. When they finally compared the photographs, the stars had moved exactly as Einstein predicted, almost overnight. Albert Einstein became one of the most famous scientists on Earth. But that was only the beginning. Over the following century, experiment after experiment continued confirming his theory. Today, every time you open a map on your phone, you're using Einstein's gravity. GPS satellites orbit Earth nearly 20,000 kilometers above your head. Because gravity is weaker there, time flows slightly faster for the clocks on board those satellites than it does for clocks on Earth's surface. The difference is tiny, only about 38 microseconds every day, but without correcting for Einstein's prediction, your GPS location would drift by nearly 10 kilometers every single day. Your navigation works, and because Einstein was right, the universe itself keeps confirming his equations. We also discovered something even stranger. Massive galaxies don't simply pull on nearby objects, they bend the very path of light traveling across the universe. Imagine looking through the bottom of a wine glass. Objects behind it appear stretched, distorted, sometimes even duplicated. The universe does exactly the same thing. Entire galaxies become natural cosmic lenses, magnifying even more distant galaxies hidden behind them. This phenomenon is called gravitational lensing, and we've now observed it thousands of times. Einstein predicted it decades before our telescopes were powerful enough to see it. Then came another astonishing confirmation. For generations, black holes existed only on paper. Einstein's equation suggested that if enough mass was squeezed into an unimaginably small region, space-time would curve so dramatically that nothing could escape, not even light. Many scientists thought such objects could never really exist. Until nature proved otherwise, astronomers found stars orbiting invisible objects far too massive to be anything except black holes. Then, in 2019, humanity captured the first direct image of a black hole's shadow, a blurry ring of glowing gas surrounding complete darkness, exactly the kind of image Einstein's equations predicted. And still, the confirmations continued. In 2015, scientists detected something many believed would remain impossible forever. Gravitational waves, tiny ripples traveling through space-time itself. More than 1 billion years ago, two enormous black holes collided. The collision released more energy in a fraction of a second than all the stars in the observable universe combined. That violent event stretched and compressed space itself. By the time those ripples reached Earth, they had become unimaginably small. The LIGO observatory measured distortion smaller than the width of a proton, an achievement so extraordinary it seemed almost impossible. Once again, Einstein had been right. After more than 100 years, every major prediction of general relativity has survived experimental testing. And that's exactly what makes the next problem so disturbing, because despite all its success, Einstein's theory cannot be the final answer. Not because a theory is wrong, but because it becomes impossible to use under the most extreme conditions in the universe. To understand why, we have to enter a world where Einstein's elegant universe begins to fall apart. A world unimaginably smaller than atoms. The quantum world. Quantum mechanics described reality at the smallest scales with astonishing precision. It explains atoms, electrons, light, chemical reaction, and nearly every piece of modern technology surrounding you. Without quantum mechanics, there would be no computers, no lasers, no smartphones, and no internet. Like Einstein's theory, quantum mechanics is one of the greatest scientific achievements ever created. But there's a problem. The universe only has one reality. And yet our two greatest theories describe it in completely different ways. Einstein's universe is smooth, continuous, elegant. Space-time behaves like an endlessly flowing fabric. Nothing is fundamentally broken into pieces. Quantum mechanics tells a completely different story. At unimaginably tiny scales, nature becomes uncertain. Particles behave like waves. Empty space boils with virtual particles constantly appearing and disappearing. Nothing stays perfectly still. Instead of a calm fabric, and reality resembles a restless ocean. Physicists believe that at a distance called the Planck length, around 10 to the minus 35 meters, space-time itself may no longer be smooth. Instead, it may become violently turbulent, like looking at the surface of the ocean from an airplane. From high above, it appears perfectly flat, but fly close enough, and you discover endless waves, foam, spray, and chaos. Space-time may work exactly the same way. From our everyday perspective, it appears smooth, but deep beneath reality is it could be made of tiny quantum fluctuations, constantly changing from one moment to the next. This picture is often called quantum foam. And here's where physics reaches its breaking point. Einstein's equations assume space-time is perfectly smooth. Quantum mechanics assumes reality is fundamentally uncertain. When physicists try to combine both ideas into a single equation, the mathematics explodes. Instead of meaningful prediction, the equations produce infinities, infinite energy, infinite curvature, infinite probabilities. Numbers that cannot exist in the real universe. Whenever infinity appears in physics, it's usually a warning. Not that nature is infinite, but that our understanding is incomplete. It's as if two puzzle pieces fit perfectly with every other piece, yet refuse to fit together with each other. Both theories are astonishingly successful. Both are experimentally verified, and yet they cannot both be the complete description of reality. Somewhere beneath both theories, something deeper must exist, something we've never fully discovered. And that realization forced physicists to ask one of the boldest questions ever imagined. What if gravity itself must become quantum? What if gravity, just like light, is carried by its own fundamental particle, a particle no one has ever seen, a particle known only by its name, the graviton? What if gravity is carried by its own particle, a particle no one has ever seen, a particle that has never been detected, a particle known only by its name, the graviton? At first, the idea sounds perfectly reasonable. After all, every other fundamental force in nature has its own messenger. Electromagnetism is carried by photons. The strong nuclear force is carried by gluons. The weak nuclear force is carried by the W and Z bosons. These tiny particles transmit forces from one object to another. So why should gravity be any different? Perhaps gravity also has its own messenger, a particle constantly exchanged between every object with mass, an invisible carrier moving silently through the universe. Physicists call this hypothetical particle the graviton. If gravitons exist, they would finally allow gravity to fit into the language of quantum mechanics. General relativity and quantum physics could become part of one unified framework, one elegant theory describing everything. For decades, this seemed like the obvious solution. There was only one problem. Nobody could find one. Not in particle accelerators, not in underground laboratories, not in space, not anywhere. And the reason is almost unbelievable. Gravity is unimaginably weak. Take a simple refrigerator magnet. That tiny magnet, small enough to fit in your hand, can easily lift a paperclip against the gravitational pull of the entire Earth. Think about that. The whole planet is pulling downward, yet a tiny magnet wins effortlessly. That's how weak gravity really is. If gravitons exist, they interact so weakly with matter that detecting even a single one may be practically impossible. Some physicists have estimated that building a detector capable of observing one graviton directly would require an instrument so massive it might collapse into a black hole before the experiment even began. In other words, nature may have hidden gravitons behind a wall that technology can never cross, but the mystery becomes even deeper. There is one modern theory that naturally predicts gravitons: string theory. Unlike ordinary physics, where particles are treated as tiny points, string theory imagines that every particle is actually an unimaginably small vibrating string. Just as different notes emerge from different vibrations of a guitar string, different particles emerge from different vibration patterns. One vibration becomes an electron, another becomes a photon, another becomes a quark. And remarkably, one specific vibration naturally behaves exactly like a graviton should. It has all the mathematical properties physicists were looking for many researchers. This was exciting. Perhaps gravity wasn't missing after all. Perhaps we had simply been looking at reality from the wrong perspective. But once again, there was a problem. String theory predicts many beautiful things, yet none of them have been experimentally confirmed. No vibrating strings have ever been observed. No extra dimensions have ever been detected. No graviton has ever appeared in any experiment. The mathematics is elegant. The ideas are breathtaking, but nature has remained silent, and that's something good science never ignored. A beautiful theory is not automatically a true theory. Physics doesn't reward the most elegant idea. It rewards the idea that survives experiment. So today, the graviton remains exactly what it has always been: a fascinating possibility, not an established fact. But then some physicists began asking an even more dangerous question. What if we've been trying to quantize the wrong thing? What if gravity doesn't need its own particle because gravity isn't fundamental in the first place? That idea changes everything. Imagine watching a stadium filled with 50,000 people. From above it, you notice something extraordinary. And a giant wave moves around the entire stadium. It looks alive, almost like a single object traveling through the crowd. But if you look closely, there is no actual wave. Each person simply stands up, then sits down. The wave isn't a thing. It's a pattern. It emerges from thousands of individual actions happening together. Now think about temperature. Temperature feels like a real property. The cup of coffee is hot, so ice is cold. But individual molecules aren't hot or cold. Each molecule is simply moving. Temperature emerges only when billions upon billions of molecules move together. Heat isn't fundamental. It's an emergent phenomenon. Traffic jams work the same way. No driver creates the traffic jam. Yet somehow, a wave of slowing cars appears. It moves backward along the highway, almost as if the traffic jam has become its own physical object. But it hasn't. It's simply a large-scale pattern emerging from countless individual behaviors. And that raises an astonishing possibility. What if gravity works exactly the same way? What if gravity isn't one of nature's basic ingredients, but a large-scale pattern emerging from something far deeper? That question led Dutch theoretical physicist Erik Verlinde towards one of the most controversial ideas in modern physics. In 2010, Verlinde proposed something extraordinary. Gravity may not be a force at all. Instead, that it may emerge naturally from entropy. To understand why, we first need to understand what entropy really means. Entropy is often described as disorder, but that's only part of the story. A better way to think about entropy is possibility. Imagine opening a bottle of perfume in one corner of a room. At first, all the perfume molecules are concentrated in one small space, but slowly they spread throughout the room. Nobody pushes them. Nobody tells them where to go. They simply move toward the arrangement with the greatest number of possible microscopic configuration. The highest entropy state. Now imagine stirring cream into a cup of coffee. The cream mixes completely. You never see it spontaneously separate again, and not because it's impossible, but because the mixed arrangement is overwhelmingly more probable. Nature naturally moves towards states with more possibilities, more microscopic arrangements, more entropy. Verlinde asked a breathtaking question. What if falling objects aren't being pulled by gravity at all? What if they're simply moving toward the most probable arrangement allowed by the universe? What if gravity isn't a force, but the statistical behavior of information organizing itself? That sounds almost unbelievable. But the mathematics behind the idea turned out to be surprisingly powerful. Not because it proves gravity is emergent, it doesn't, but because it reproduces several known properties of gravity using information and entropy instead of a fundamental force. For the first time, gravity began looking less like a basic interaction and more like a consequence, a shadow, an emergent behavior arising from something even deeper. And once again, that deeper layer pointed toward the same mysterious word that has been quietly following us through this entire series: information. Because if entropy measures information and gravity emerges from entropy, then perhaps gravity itself, it is ultimately born from information. And if that's true, we're about to uncover a connection so strange that it completely changes the way physicists think about black holes, space-time, and reality itself. Kamkala Ekanamra, Episode 6 of Species Dishali Anthealiki, Economy of Storytelling, Tiktaak, Doshek Pediocious Prindekbe, Tayami Part 40, Netflix documentaries, Tidile Aro, Cinematic EBN Bijnyanik Bahabi, Balanced Krechi Dalha. Perhaps gravity itself is ultimately born from information. If that's true, then one place in the universe should reveal that connection more clearly than anywhere else. Black holes, few objects in nature, have fascinated physicists more. Imagine compressing so much mass into such a tiny region of space that gravity becomes overwhelming, so overwhelming that nothing can escape. Not matter, not light, not even time behaves the way we expect. For decades, the black holes seemed like the ultimate prisons. Anything that crossed the event horizon was gone forever. At least, that's what everyone believed. Then in the early 1970s, a young physicist named Jacob Bekenstein asked a question that almost everyone thought was ridiculous. If black holes swallow everything, what happens to entropy? At the time, many physicists believed black holes had no entropy at all. They were thought to be perfectly simple objects, just mass, electric charge, and spin, nothing else. But Bekenstein disagreed. He argued that black holes must possess entropy. Otherwise, they would violate one of the deepest laws of physics, the second law of thermodynamics. According to that law, the total entropy of the universe can never decrease. If entropy simply disappeared inside black holes, the law would be broken, and the foundations of physics would collapse. Bekenstein proposed something astonishing. The entropy of a black hole isn't determined by its volume. It's determined by the area of its surface. That idea sounded completely absurd. Everything we know about everyday objects depends on volume. A larger room holds more air because it has more volume. A larger bottle holds more water because it has more volume. Why would a black hole be different? Years later, Stephen Hawking decided to test Bekenstein's idea. Ironically, he expected to prove it wrong. Instead, he discovered something even stranger. Using quantum mechanics, Hawking showed that black holes are not completely black. Tiny quantum fluctuations near the event horizon allow black holes to emit an incredibly faint glow. Today, we call it Hawking radiation. That discovery shocked the scientific world because if black holes emit radiation, they slowly lose energy over unimaginable periods of time, and they eventually evaporate completely. But then, a terrifying question appeared. If a black hole disappears, what happens to everything that fell inside it? Every atom, every photon, every piece of information. Does it vanish forever? That question became known as the black hole information paradox, and more than 50 years later, it remains one of the greatest unsolved problems in theoretical physics. Here's why it matters. Quantum mechanics tells us that information cannot simply disappear. The evolution of a quantum system preserves information, destroys information, and the mathematical foundations of quantum mechanics begin to fail. General relativity, on the other hand, appears to allow black holes to erase information forever. Both theories have overwhelming experimental support, yet here they directly contradict each other. One of them must be incomplete, or perhaps both are missing something deeper And that's exactly where gravity, entropy, and information suddenly become inseparable. Because Hawking made another extraordinary discovery. When he calculated the entropy of a black hole, he found something nobody expected. The entropy depends only on the surface area of the event horizon, not the volume hidden inside. Think about that. Everything that has ever fallen into a black hole, every star, every planet, every particle, every photon could, in principle, be encoded on a two-dimensional surface, almost like the universe is storing three-dimensional reality on a flat cosmic screen. Does that sound familiar? It should, because in the previous episode, we explored an idea called the holographic principle, the proposal that our three-dimensional universe may actually emerge from information encoded on a lower dimensional boundary. Originally, that idea sounded almost philosophical, but black holes changed everything. Suddenly, the mathematics began pointing toward exactly the same conclusion. Perhaps information really is more fundamental than space itself. Perhaps space, volume, distance, and even gravity are all emergent consequences of how information is organized. Notice something remarkable. Every path we've taken throughout this series keeps leading back to the same destination. Quantum mechanics and wave functions, measurement, entropy, black holes, space-time, gravity. Every road seems to converge on one mysterious concept: information. Not information in the everyday sense, not emails, not computer files, not text messages, but information is the fundamental distinction between possible states of reality. Some physicists have even suggested that the universe behaves less like a machine and more like an unimaginably vast information processing system. That doesn't mean the universe is literally a computer. It means that information may be the deepest language nature uses. But this is where we have to be careful. Here's what experiments actually tell us. We know black holes exist. We know gravitational waves exist. We know Hawking's theoretical prediction of black hole radiation is one of the most important results in modern physics. Although the radiation itself has not yet been directly observed from astrophysical black holes because it is extraordinarily weak, we also know that black hole thermodynamics has survived decades of theoretical scrutiny. What we do not know is whether information truly escapes every black hole. We do not know whether the holographic principle literally describes our universe, and we certainly do not know whether gravity itself emerges from information. These remain active areas of research. Some ideas are strongly supported mathematically. Others remain hypotheses. Good science recognizes the difference, but here's what makes this mystery impossible to ignore. The deeper physicists investigate gravity, the more often information appears, almost as if gravity is pointing towards something hidden beneath reality. And once you notice that pattern, another mystery begins to emerge. Because if gravity is connected to information, could the greatest mysteries of the universe, dark matter and dark energy, also be telling us the same story? And that's where our journey takes its next unexpected turn. Ekan Part 5, Heish Garby, Episode 6, The Cinematic Ending. Ekan, Dark Matter, Dark Energy, Information, Reality. SB Exata Connect, HBEBN, Episode 70, GDNY, Shktishiyali. Cliffhanger, Tyree Corby. Oh, whoa. For decades, astronomers believed they understood how the universe moves. Gravity pulls matter together. Stars orbit galaxies. Galaxies orbit clusters. Everything seemed predictable until they looked more carefully. When astronomers measured how fast galaxies rotate, they found something impossible. The outer stars were moving far too fast. According to everything Einstein and Newton had taught us, those galaxies should have flown apart billions of years ago. But they didn't. Something invisible, something massive, was holding them together. No telescope could see it. No instrument could detect it directly, yet its gravitational influence was undeniable. Physicists gave this unseen ingredient a name: dark matter. Not because they understood what it was, but because they had no better explanation. Then, just as scientists were beginning to accept dark matter, the universe revealed another surprise. In 1998, two independent teams studying distant supernovae made an astonishing discovery. The expansion of the universe wasn't slowing down, it was speeding up. Gravity should have been pulling galaxies together. Instead, the universe itself seemed to be pushing everything apart. Something was overcoming gravity on the largest scales imaginable. Again, nobody knew what it was. Again, physics invented a name: dark energy. Today, these two invisible components dominate our understanding of the cosmos. According to the best measurements we have, everything you've ever seen, every planet, every star, every galaxy, every atom in your body, accounts for less than 5% of the universe. Roughly 27% appears to be dark matter. Around 68% appears to be dark energy. Together, they make up almost the entire universe. Yet we still don't know what either one actually is. Think about that. Modern civilization has mapped the human genome, detected gravitational waves, photographed the black holes, built quantum computers, and yet about 95% of reality remains fundamentally mysterious. Some physicists believe dark matter is made of undiscovered particles. Others search for entirely new quantum fields. These are serious scientific efforts supported by decades of research. But another possibility has quietly emerged. What if dark matter isn't matter at all? What if we're simply misunderstanding gravity? If gravity is an emergent phenomenon, if it arises from information rather than existing as a fundamental force, then perhaps galaxies only appear to contain invisible matter. Perhaps what we're seeing is gravity behaving differently when information organizes itself across enormous cosmic distances. This idea remains controversial. It has not replaced the standard model of cosmology, but it demonstrates something important. Even our greatest mysteries may ultimately point toward the same hidden foundation: information. The same possibility appears when physicists discuss dark energy. Instead of imagining an unknown energy filling empty space, some researchers ask a different question. Could the expansion of the universe emerge naturally from the way information evolves? Could space itself respond to information rather than simply existing as an empty state? No one knows. The evidence is still incomplete. But once again, gravity, space-time, entropy, and information refuse to separate. Every path seems to lead back to the same place, almost as if the universe is quietly repeating the same answer, while we're still trying to understand the question. And perhaps that's the real lesson. Throughout this entire series, we've peeled away layer after layer of reality. We began with quantum uncertainty. We explored entanglement. We questioned observation itself. We discovered that space-time may emerge from something deeper. We followed gravity into the world of entropy, and every time, the trail pointed toward information, not as technology, not as human knowledge, but as something woven into the deepest structure of existence. If that picture is even partially correct, then gravity isn't simply pulling planets toward stars. Gravity may be the universe organizing information into structure. Space may be information appearing as geometry. Matter may be information appearing as particles. Reality itself may be information taking form. But one final mystery still remains. We've asked whether matter is fundamental. We've questioned space. We've questioned gravity. We've questioned information itself. Now only one question remains. If information lies beneath everything, what lies beneath information? Is information truly the final foundation of reality? Or is it simply another layer hiding something even deeper? Some physicists believe reality is ultimately mathematical. Others believe information is the bottom layer. Some think space, time, matter, and information all emerge from an even more fundamental quantum structure we have not yet discovered. Right now, no experiment can answer that question. Not yet, but history teaches us something remarkable. Every time humanity believed it had reached the deepest level of reality, another deeper layer appeared. Perhaps we're standing at that boundary once again. Perhaps the greatest discovery in physics hasn't happened yet. And if that's true, then everything we've learned so far may only be the beginning. Because in the next episode, we ask the biggest question the series has ever faced. If matter isn't fundamental, if space-time isn't fundamental, and if gravity isn't fundamental, and if information may not be fundamental, then what is? What is the universe actually made of? And if we ever discover that answer, we may finally understand not only how reality works, but why reality exists at all. I'll see you in the next episode.